Hi everybody, welcome back. We've talked so far about Newton's laws, or two of Newton's laws. We mentioned how there's three of them. And we talked about his first law, which is that law of inertia, and the second law being the law of, that is force, net force is equal to mass times acceleration. Now this is his third law right here. We oftentimes refer to it as the action-reaction law, and it's frequently said for every action there is an equal and opposite reaction. And what that means is, for every action, well, that action is a force. For every force that acts on some object, object 1, we'll say, all right, or maybe I'll underline that in red, on an object, there is a reaction force acting on a different object. So this is like object 2, I'll make that green, that the force is equal in magnitude, but it's opposite in direction. All right, action-reaction is equal and opposite. So I'm going to do a little kind of sketch right here to illustrate that. So for objects that are touching each other, there's going to be equal yet opposite forces acting between those objects. All right, let me move this back up there a little bit like that. Okay, let's just say this person right here, okay. I'm going to draw a person. They're going to have their hand out. This is going to be kind of an ugly person, all right? They got their hand out like that. It looks like Gumby or something like that. They got their hand out like that, and they're pushing. This is person 1, okay? Or person A, I should say, all right? They are pushing with a force that way. Force from A, and I'm going to mark that up a little bit more in just a second. All right, and it's being applied to another person, person B. All right, so this is person B right here. Equally ugly, oops, weird leg. Equally good person, fat leg right there, okay. And they are applying a force this way. So this is person B. Right there. All right? So that's force from person B. But that force from person B, and I'll put a little vector symbol over that, is being applied to A. Let me erase that little thing right there. I'm going to erase this whole thing. Force from B to, there's a little arrow there, B onto A, and the person, the green A person, is applying a force to person B. All right? What is true about these two forces is that they are equal in magnitude. This one I'm about to write cannot happen. You cannot have two people contacting each other, so there's a contact between their hands right there. You cannot have one person say, I'm pushing harder. It looks like harder right there. You can't have that. Speech balloon right there. Why can you not have that? Because Newton's third law tells us that, and likewise, this person can't say that as well. Newton's law says that whatever force is being felt on the green person's palm, being applied to the red person B's palm, is the exact same force that person B, his palm, is feeling by applying a force on a person A, who is red, okay, or sorry, who is green. So they both have to have the same force being applied between those two surfaces right there. It doesn't have to be surfaces. It could, well, in most cases it will be surfaces, but there's some subtle differences. But the idea is that the force from A to B, and I have that, I have the wrong color, don't I? It should be green. The force from B to A is the same magnitude, but the key difference here is that it is in the opposite direction. It's negative. So I don't care what direction you call positive in this little scenario that I drew right there. If we call, I don't know, that positive and this direction negative right there, then you would say force from person A onto person B would be positive, and that would be have to equal and be opposite to the force from person B pushing onto A. Equal in magnitude, but opposite in direction. So we call those contact forces. The contact force between any two surfaces is always going to be equal. However, they are going to be opposite. All right? So let's see if we can apply that to an example right here. And then that'll be it for this segment. Okay? So this is example 5.5, and here we have some canoeists in a lake. All right, now once again, I'm going to take this, I'm going to read it, go over it, and I'm going to shrink it down so we have a little bit more space to write. All right. So here we had two groups of canoeists meeting, oops, I'm going to do that, in the middle of a lake. All right. So they brief, they visit, they talk, and after a while, the canoe one person pushes on canoe two with a force of 46 newtons. Okay, so he's going to apply a force in that direction. So we should really call this force from 1 to 2, and of course the opposite, equal and opposite force would be force from 2 to 1. Okay, so this is canoe 1 and this is canoe 2 right here. Let's see. We should really call this should really, in my opinion, this should be called force 1, this should be called force 2, but either way, we're going to give it different labels anyway, all right? So, let's just finish reading it. So, person from canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes, okay? The canoes obviously have different masses, right, because they've got different numbers of people in each canoe. The mass of canoe 1 is 150 kilograms. This canoe 2, is 250 kilograms. All right? We're going to find two things. We're going to find the acceleration that the push gives to each canoe. In fact, what I'll probably do is this segment, I'll just make this part A, and then I'll save part B for a subsequent segment. Okay? But part B is asking, what is the separation of the canoes after 1.2 seconds of pushing? All right, so it's applying a constant force in part B for 1.2 seconds, and the canoes are separating apart in that amount of time. All right, and that's going to bring kinematics into it right there. But for now, let's just take this and solve for the acceleration to each canoe. I'm going to take this and shrink this down here. All right, and so just like I drew with my weird-looking stick people in the previous slide, let's make two canoes. We're going to call this, it's canoe 2. All right, and that's got a bunch of people in it. And canoe 1 is going to be red, and that's going to be over here. Okay, and it's only got a few people in it, like so. All right. Now, I left a little space in there. I guess I could have, let's see here. Maybe I can take this and move it around. Nope, I've got to move the whole thing. All right. Anyway, that's all right. We have a little space to draw our forces. So what's happening here is this person in canoe 1 is applying a force, and he's stretching out his arm, and he's applying a force over to canoe 2. I'm not going to draw that because it might get a little bit just crowded, but I'm going to draw the forces in here. So the force from 1 to 2 equals 46 newtons, all right, being applied to canoe 2. And according to Newton's third law, there is an equal yet opposite force from 2 to 1, I'll make that a vector, equals 46 newtons, but in the opposite direction, so I'm going to make that negative 46 newtons. Okay? Negative 46 newtons. That's being applied to canoe 1. Canoe 2 is receiving the same, but they have different masses, and so we're going to have different accelerations. All right? So we're going to say for canoe, what color am I in right here? For canoe 1. Okay? For canoe 1, the mass of canoe 1 is 150 kilograms. 150 kilograms, and the acceleration of 1 is what we want to solve for. Okay? What's the net force? The net force being applied to canoe 1. Well, it's the force that's coming from the contact between 1 and canoe 2. So it's really a contact force coming from canoe 2 that is pushing back on canoe 1. So that is going to be this negative 46 newtons. All right. So even though it's canoe 1, it's kind of, you might say, receiving a force, or receiving a reaction force of negative 46 newtons from, in fact, you know what? I'm going to draw this. I'm going to write force from 2 to 1, right? It's being applied to canoe 1 of negative 46 newtons. Well, we can solve for acceleration pretty easily. If we know that the net force on an object equals the mass of that object, mass of 1, times acceleration of that object, then our acceleration is going to be the net force divided by the mass. So this is going to be our negative 46 newtons. And I should have put my acceleration vector arrow right there. Vector, because the acceleration of that canoe is really going to be the same direction as the direction of the forces being applied to it. Right? Acceleration and force are both vectors. Mass is just scalar, so whatever direction the force is coming from, going that way, this way from canoe 2, that's the direction that the canoe 1 is going to accelerate in. Okay? So the net force on canoe 1 is equal to negative 46 newtons. Take that and then divide that by the mass of canoe 1. So that is 150 kilograms. And all we have to do is do a little bit of calculation, and we will have our acceleration. So negative 46 divided by 150, I get a negative 0.3 something, 0.307. It's probably too many sig figs. I'm going to make that 3.1. 0.31 meters per second squared. Meters per second squared. That's our acceleration of canoe 1. All right. It has just 2 guys in it. Now let's kind of predict what we expect our acceleration of canoe 2 to be. All right, well, it's going to have the same amount of force, but a different direction applied to it, but it's going to be applied to more mass, and so we should probably expect that the acceleration is going to be less for canoe 2. Well, let's go ahead and find out. For canoe 2, the mass of canoe 2 equals 250 kilograms. All right, the acceleration of 2 is what we want to find, and the net force on 2 is really the reaction force that we get from canoe 1. That's the force from 1 being applied to canoe 2, and that is positive 46 newtons. Okay, we know our net force on canoe 2 is going to be the mass of canoe 2 times the acceleration of canoe 2. And by the way, there's our vector lines right there. So we know that whatever direction the force being applied to canoe 2 is coming from, that's what the direction the acceleration is going to be in as well. So we're going to expect canoe 2 to move that way. That's all for our acceleration. Our acceleration on canoe 2 is going to equal the net force on canoe 2 divided by the mass of canoe 2. That is going to be 46 newtons. 46 newtons being applied to canoe 2 divided by the mass of canoe 2, which is 250 kilograms. All right, so our acceleration of canoe 2 is going to be something very different. That's going to be 250, and that's going to be 0.184. 0.18, we'll say, meters per second squared. All right? It's going to be in the opposite direction as indicated by, there's no negative right here, so this is a negative direction, but clearly this is a greater acceleration than that. Either way, they're not accelerating very rapidly, but this is almost twice what this is right here because of the difference in mass. Okay? So, that's part A, an example HPhy1, the canoe problem. I'm going to continue with part B in the second one. This is going to bring kinematics into it. Now that we know our accelerations, we should be able to find the separations of the canoes pretty easily after 1.2 seconds. All right, but that's going to be part B, and I'll see you on that one. Thanks for following along.